Okay, good day students. Today we'll be looking at our unweighted assessment on heat, water changes of state and water cycle. We will start off with section B, your open-ended question. So question 13A, state a difference, okay, between evaporation and boiling. So I've said this many times that these two processes are very different. So they both will actually form water vapor, but the water vapor are at different temperatures. So what is common? Okay, the common fact between both of them is that they both would form water vapor. Same thing. But the difference is that your water vapor for boiling is at 100 degrees Celsius. Alright? Now, on top of that, your evaporation and boiling, what can you say? That is very, very obvious. Now, the first thing is that your evaporation takes place at any temperature below boiling point. So I'm going to pen that down for you. Okay, now when you are stating a difference, please use contrasting words such as but, while, okay, or however. Now also be very careful with your degree Celsius. Make sure you have written it with a small dot at the top. Okay, some of you, your degree Celsius looks like this, okay, for your degrees. Alright, now, other acceptable answers, please pen this down if you do not have it. I think it's good, okay. Evaporation takes place at the surface of the water. Okay, but boiling takes place throughout the water. And how do you see it? It's through the formation of your bubbles. Okay? Now, please be very careful. You cannot say that evaporation produces water vapor and boiling produces steam. Alright, because essentially they are the same thing. It's just that boiling is at the water vapor that it produces is at 100 degrees Celsius. Alright? So keywords will include things like wow and but. Now, moving on to the next question. John was having a fever. The doctor advised his mother to place a cooling pad. So right off the top, I see fever, I see cooling pad. Okay, over his forehead to cool his forehead. So what comes to my mind would be, a fever means that he is having a higher temperature. Right? And the cooling pad tells me that this is my region of lower temperature. Okay? So when I'm answering this question, I would like to ask myself, what is this topic? This topic is actually on heat, and the concept that they are testing you would be heat transfer. So straight away, you should recall that for heat transfer, heat always travels from a region of higher temperature to a region of lower temperature. Right? So with that in mind, we can then answer the next question. Explain how the cooling pad helps to cool John's forehead. So in order for a region to be cooler, it must have lost heat. So lost heat to where or to who, right? So in this case, it will be lost heat to the cooling pad. In fact, the statement already tell you, cooling pad helps to cool. So straight off the bat, the question already told you the answer. Right? So how can we then translate that into our answer? So you can say the cooling pad gains heat from John's forehead. So I will accept it if you tell me that it's John's body or just John itself, because John itself includes his forehead. So 1 mark for telling me the direction from where to where. Okay, and then another mark for identifying the correct cooler and warmer regions. Okay, so I've repeated myself many times. Whenever it comes to heat transfer, be it a direct heat transfer question like such, or when you're talking about an evaporation question whereby the water source needs to gain heat, you have to identify where is the source of higher temperature, okay, and then where does the heat flow to the cooler region. Alright, so that is very important, something that I have reiterated many times. Okay, moving on. Next, the diagram below shows some water droplets that Paul found on the surface of his car at 5:30 in the morning. So straight off the top, I see water droplets. It would signal me that it's a question on condensation. Condensation has occurred. Very straightforward. And so what should come in your mind would be the common things like, oh, in order to even have condensation to happen, I need water vapor. The water vapor must touch a cooler surface, it needs to lose heat to it, and then it has to condense into water droplets. Very standard condensation question. No doubt about it. Alright? So, let's move on. State the change of state. Now, this is a very problematic question. Okay? Now, a lot of students have not answered this question or have misread this question. Instead of telling me the change of state, students have instead told me the process, which is condensation. No. Okay, so ask yourself, state. What are states? States will be solid, liquid, gas, right? Solid, liquid, and your gas or gaseous state. So from what to what? So like I told you, water vapor touches a cooler surface. Water vapor is what? It's a gas, right? Okay. And then after that, condense into water droplets. Water droplets is liquid. So it's gas to liquid. Because of this, many careless marks were lost. B. Explain how water droplets got onto the surface of the car. Now, this is a very typical condensation question. The only tricky part is that you need to know, okay, where is the source of your warmer water vapor? That is the part that many of you could not get it. So, take a look at this. It says on the surface of the car. So with this, I'm going to spend some time to explain about this question. So to help us with that, I'm going to draw a car for us. Now, the fact that he found the water droplets on the car, on the outside of the car, okay, tells me that the warmer water vapor is actually, okay, from the surrounding. Okay, from the surrounding. from the surrounding air. Okay, maybe I should use a different color to denote warmer water vapor. Yeah, my apologies. Let me change to a warmer color. Okay, now where is this water vapor? This water vapor is in your surrounding air, because air is basically a mixture of different type of gases. One type of your gases is actually water vapor. So you have to tell me, where did the water vapor come from? You cannot just say water vapor. You know why? Because the water vapor also exists inside the car, right? Because inside your car would also have air, and if it has air, that means water vapor is also present. But in this case, they say on the surface, so we assume that it's outside. So if the water droplets are from outside, the water vapor has to come from the same side where you found your water droplets. Okay? So therefore, your answer would be water vapor from the surrounding air touches the cooler surface of the car, lost heat, and condense into water droplets. Now over here, this part, if you really want to be very clear, you can say lost heat to the surface of the car. Now, so what are my marking points for this time round? I'm looking from water vapor from where? I am also then looking for cooler surface. I'm looking for lost heat. And I'm looking for condensed into water droplets, half mark each. Now, many of you have also forgotten lost heat. For some very appalling reasons, you have forgotten that, even though I reminded you. Next. Paul found that the water droplets were no longer on his car at 9 a.m. So straight off the top, water no more. So it can only mean one thing: evaporation has happened. Well, another thing would be someone used a piece of cloth to wipe it. But obviously that's not the answer we are looking at. If it just disappears like that, it probably means that it has evaporated. It's as simple as that. So you have to talk about evaporation. And with evaporation, you will need heat gain. So with heat gain, I always remind you all this thing, right? Where is the source of the heat? The direction of heat. From where to where? So at 9, so you realize that there is actually a contrast between the two times, 9 a.m. and 5:30. So at 9 a.m., we think about what is the difference between 9 a.m. and 5:30. The most obvious would be the sun has come out. Now, be very careful. Some of you actually said gain heat from sunlight. That is not correct. Your sunlight is just light energy. Light energy and heat energy are two completely different types of energy. You can say gain heat from the sun, but you cannot say gain heat from sunlight. Okay, be very careful about that. Okay, and then they went on to say, explain what had happened. So how to translate this? Very straightforward, correct? So you would say that the water droplets gained heat from the sun, okay, or surrounding, I will accept both, and evaporated into water vapor. Okay, marking points would be gain heat from where, as well as evaporated into water vapor. Half marks for each point. Okay. Next. Okay, next. This is quite a common question actually. Many of you could not answer this question because you use the wrong keywords or you have misunderstood what you are writing. So it is very important to be careful to write what you mean. Alright, because your writing would tells me a totally different thing. So let's take a look. Joshua placed two identical pots A and B on two metal plates of the same material. 500 ml of water at room temperature was poured into each pot. Okay, and the metal plates were heated from below. Okay, now, so you take a look at these two items. You look at these two experiments. The main difference between these two would be that your metal plate Y and your metal plate X are different. How are they different? They're different in the sense that if you take a look at metal plate Y, the only points that were in contact are the ones that are colored in red. And then, those places where I shaded green, your pot is not in contact. So in short, I would say that your metal plate X has more surface in contact or more surface area in contact with the pot. Now what most of you said was metal plate Y has more exposed surface area. Oh, sorry. Yes, you said something like that, which is not correct. Right? It's not about exposed surface area. It is about area in contact with the pot. It's touching the pot, not being exposed. It's got nothing to do with that. Okay? Yes. So, sorry. Thank you for pointing it out. Actually, it's less surface area. Okay? Less surface area in contact with the pot. Right? Less. Because if you take a look at it, these areas here are the areas that are in contact. As compared to this side has more surface in contact. Right? So when you think about it, since there's more surface in area in contact with the heating plate, there is also a greater surface for heat to be conducted from your metal plate to your pot A as compared to pot B. Right? So, in your answers, I shouldn't be seeing exposed surface area. I should be looking at the concept of surface area in contact. Now, how would I pen this down? Okay, so one other very important thing, okay, you need to actually talk about how about B, okay? So if you just talk about A, it's also not correct, alright? So how do we compare this? So there are two parts to this answer. The first part is comparison about your surface area in contact. So I would say that metal Y has, metal plate Y. Metal plate Y has a smaller surface area in contact with port B as compared to metal plate X with port A. Okay, so in this case, we need to compare smaller. Now, then the second part, you talk about the rate of heat transfer. So part 2, I would say that then heat or less heat gain at a slower rate from metal plate Y to port B. Okay. Okay, next question. Joshua noticed that the handle of the cooking pot was made of metal. He suggested to his brother that a plastic handle would be more suitable to make the handle. Do you agree with him? Explain why. So what is the question asking you is basically to contrast between these two materials, right? Okay, what is the difference? So the difference is one is a good conductor and the other is a poor conductor. Now the keywords to use would be poor and good. Some of you say bad conductors. That's not right. Okay, let's try and be consistent with the conventional naming. Now, we also need to take note that conductors of heat is a relative thing. So you must always compare and contrast. So for example, if I give you another question, they are both metals. Say example, iron and gold. Then how? You cannot say iron is a good conductor of heat and gold is also a good conductor of heat. You cannot. It's better, right? So similarly from here is good practice. So I would say that you should use the word poorer or better conductor of heat. Okay? So how would I translate the first part? So let me explain the first part first. So first part is a comparison, right? So I would say the plastic handle, or rather I should use plastic. Sorry, change that. I think better to just say plastic is a poorer conductor of heat as compared to metal. So this is the first point. Now, then after that, you must tell me, so what? Now, whenever you talk about conductors of heat, the concept tested here is conductors of heat. You are concerned with the rate that heat is being conducted. Okay, through this material. So you have to talk about rate of heat transfer. Definitely is a confirmed thing. So the next part, that's what you need to talk about, right? Now, the next part is that most of you have gotten the part about heat would then be transferred to the plastic handle at a slower rate from the pot to the plastic handle. But don't forget, the question is that why do you want to make the handle? Who is touching the handle? The hand is touching the handle. So the reason why you want a poor conductor is so that your hand does not get burnt. So you will also have to say that heat will also be conducted at a slower rate, okay, to the user's hand. So the user's hand will not be burnt. So that point needs to be there. Okay? Alright, so that is very important. Okay? So you would say that it allows slower heat flow from the plastic handle to the brother's hands, or to his brother's hand. Okay, that is the key point that many of you are missing. Okay, inching down. Alright, next question. Darren wanted to find out what would happen when a flask of salt water was heated. He set up the apparatus below and recorded the temperature changes at various times. The room temperature was around 30 degrees. So, I guess it hints you a certain thing, right? So what is this question hinting you on with a lot of keywords? You have salt water being heated up. Okay, this would tell you that evaporation has taken place. You also have things like a crushed ice and then some liquid that's being collected. So you know that this is probably a water cycle setup. Now, when dealing with water cycle, remember there are two processes that we are very concerned with. Number one would be evaporation. Please pen this down. Number two would be condensation. So this will help you narrow down on what the question actually wants you to talk about. So what's the purpose of the crushed ice? So when you take a look at this experiment, you first ask yourself, how does the experiment run? So when the salt water is being heated up, your salt water will evaporate, right? Turn into water vapor. Okay, it will be directed into this glass tubing. Then after that, you take a look, there's this crushed ice here. So your crushed ice, right, actually causes your glass tubing to become cold. So this provides the cooler surface. So as it goes past this tubing here, your water vapor will start to condense into water droplets. And then what happens is that the water droplets, as they gather and become larger droplets, they will then drip and flow into your liquid axius, into your test tube. So liquid axia, in fact, you probably will have identified it, is actually pure water. Okay? So what was the purpose of the crushed ice, which I told you it is to give you a cooler surface. Now, the whole purpose of the crushed ice is to make your glass tubing colder or cooler. You are not supposed to describe the whole entire water cycle, which is what many of you have done so. No. Why? Why is it the key important point? Now my question to you is, what would happen if, let's just say, this crushed ice is gone? So if you remove away this portion of the crushed ice, okay, does it mean that this whole setup will not work? My answer to you is no, it will still work. What is the difference? The difference would be that the glass tube is not as cold. So condensation rate will be slower. But will condensation still happen? Yes. So basically, you need to tell me that the crushed ice is to make the glass tubing cooler, and therefore increasing rate of condensation. The whole point is to increase condensation and not to allow condensation to happen, because with or without the crushed ice, condensation will still happen, because the glass tubing, the temperature of your glass tubing is still going to be cooler than the temperature somewhere here, right? So condensation will happen. But the difference is that now with your ice is cooler, so condensation happen faster. And that is the key idea, which many of you have not correctly identified. So how do we then translate that into our answer? So the crushed ice will cool the glass tubing to increase the rate of condensation. So if you just tell me condensation will happen, no marks for that. So what are my marking point? Cool glass tubing, and the second one will be increased rate of condensation. Okay, next one, name the liquid. Okay, very straightforward. Pure water. I told you this, that you cannot say drinking water, because we can drink water from the taps in Singapore. It's perfectly fine. Is that drinking water? Yes. But is that desalinated water, which is what we're doing here? No, it's not. Because the water still has certain minerals added to it, like fluoride, okay, and chlorine and whatnot. Okay, so drinking water is not accepted. Next. Oh, this is definitely very straightforward, a water cycle question. So straight off your mind, the two processes that you will need would actually be evaporation and condensation. Right? That's about it. Now, so after a while, he observed that the water dripping into the beaker from the glass delivery tube. Okay, what are two things? So the question wants you to talk about two things that Darren can do to the setup to increase the rate of water dripping from the delivery tube. So basically, this then links us to the two processes that drives water cycle, right? So your main idea is you want your water cycle to happen at a faster rate. So there are two processes that you can tweak. Either you tweak your condensation or you tweak your evaporation. You choose one. So if you want to tweak your evaporation, then you will look at your WET acronym, okay, which is actually your wind, exposed surface area, as well as your temperature. Now, by right, an increase in any of your WET will cause an increase in your evaporation rate. However, I have told you before, you really cannot use a fan in this setup. Okay, you cannot put the fan inside here. It doesn't work that way. So we will only look at factors. Either you increase the exposed surface area of your flask or you increase the temperature. Now once again, okay, many of you didn't tell me what to do. You told me the reason, but you never tell me what to do. So again, you all tell me, oh, make the temperature higher. So you cannot do that. So if you want to say that, make the temperature higher, okay, an example would be increase the number of heat source. Okay, so this is the same thing, or you can say make the flame bigger. Okay, now this is for temperature. What about surface area? So for surface area, you can say use a wider or bigger flask. Okay, so what will happen is that when you do that, your flask will be bigger, and so the area for evaporation will also be bigger. Okay. Now, next, what about condensation? So these two are for evaporation. Let's talk about condensation now. So for condensation, right, you can say either you put crushed ice on the delivery tube. Okay, over here. Then you provide a cooler surface, increasing rate of condensation. Okay. You can say use a metal delivery tube. You can say wet the cloth. Alright. So all this would also work.